All right. Hi, everyone. I'm Guo from Imperial College. My research topic is about wire-arc additively manufactured steel bolted connections. Today's presentation is mainly about double lob shear bolted connection tests. So a small introduction for wire-arc additively manufacturing. So two previous speakers gave excellent speeches about WAM technique. So here I'm just talking about the outstanding advantages over conventional manufacturing methods, which enhance the geometric versatility, enhanced customization, increased optimization, and reduced material consumption. And when it's come to the connection design, the barriers of conventional manufacturing methods are often geometric complexity and high customization. So as you can see, it really makes WAM a very suitable design, a suitable method for connection design. And not only so, WAM also provides an opportunity to combine conventionally manufactured structural members such as beams and columns with 3D printed connections. So it's realized the marriage between traditional technique and the new techniques. But before that, a comprehensive understanding of structural performance of WAM steel members and connections is required. So in this presentation, tests on WAM double lob shear connections are printed, and the results are compared against current design standards to evaluate the applicability to apply capability to WAM steel. Some general information about lob shear connections. So we have N distance, which is the distance from the end of the plate to the center of the bolt hole, E1, and we have the width of the plate, bolt hole diameter. For the failure modes, when E1 is critical, we have shear out failure. And when E1 and B are both large, we got bearing failure. And when B is critical, we have net section tension failure. Also, if bolt is critical, we have bolt shearing failure, which is not the current concern because we are more interested in WAM plate instead of bolts. So here is a little figure to tell you the relationship between three failure modes. It really tells that when E1 is small, we have shear out failure. When B is small, we have net section tension failure. And when both are large, we have bearing failure. Before the connection test, we did some material coupon tests to investigate the mechanical property of WAM's material. We tested two types of thickness, 3 millimeters and 8 millimeters. We also investigated the anisotropy by cutting coupon from the oval plates with certain angle, 0 degree, 45 degree, 90 degree angles. And the influence of undulation is investigated by testing as-built coupons and machined coupons. As for the results of this material test, we find that thicker material always have lower strength. It might attribute to the slower cooling rate. Also, we find very slight anisotropy. As you can see in these figures, we can find some anisotropy, but not that severe. And the surface undulation would cause as-built coupon 10% lower in strength compared with machined coupons. For our test setup, we test 60 double lob shear connections in total, and each WAM plate is connected to two high-strength steel plates with a high-strength steel bolts. And specimens are printed with black background and white dots so that this speckle pattern can be captured by 4 cameras here. So these 4 cameras can record the displacement and the strain fields from both sides. As for the test outcome, we have shear out failure here, we have net section tension failure here, and we have bearing failure here. In addition to this conventional failure mode, we got end splitting failure, which you can see the end of the plate has split up in these red circles. Those are the specimens corresponding to the print layer orientation parallel to the loading direction, which means vertically in vertical direction. And here are the group of specimens, similar specimens with perpendicular printing layer orientations, so in this horizontal direction. So from this figure, we can see that the left specimen and the right specimen showed shear out failure instead of end splitting failure. It might suggest that this kind of failure mode related to more to the surface condition or surface imperfection instead of geometric proportion. Also, we got a strange type of failure mode, which we called incidental block shear failure. It happens when net section tension capacity almost equal to shear out capacity. From the figure on the right, you can see we can find the end splitting fracture here in the end, on the end, and the shear out fracture here, and the next section fracture here. As for the displacement, load displacement curve, here are 4 typical curves correspond to shear out failure, net section tension failure, bearing failure, and end splitting failure. On each curve, we got the black line for the specimens with 90-degree and printing layer orientation, and the blue line for 0 degrees. We can find clearly that there is no much difference between the 2 lines. It might suggest that even though it has different printing layer orientation, the anisotropy is not that pronounced. Also, the ultimate load is almost identical. And for the printing layer orientation, it has no influence on the failure modes for most specimens either. But for some certain case, it did have some influence on the failure mode. For this pair on the left, this pair of specimens, the left one fell in shear out and the right one fell in end splitting. And on the right pair, the left one fell in net section tension and the right one fell in shear out. Then we compared our test results with existing design equations, AS, NAS, Australia, New Zealand design code, AISI and AISC American design code. Your code, we all know that. And all this design code gives quite relatively accurate predictions that suggests that our WAM still behave as we expected. Among these predictions, we find that AISC is the most accurate one with test to predict capacity ratio 1.02. And the most conservative one is AISI with this ratio 1.17. And the differences between these 2 codes is that AISC is designed for hot roll steel and AISI is for cold form steel. And it means that our WAM steel behave more like hot roll steel. So small conclusion for this comparison, for net section tension failure, its predictions are reasonable but somewhat conservative. For net shear failure, predictions are overly conservative. And for bearing failure, it's generally quite opposite, unconservative. So what happens next is that I'm going to do more FE simulations to the lob shear connections to enrich the data pool, and then calibrate the existing equations for the suitable safety factor, or just propose new equations. And the last part is to do some optimization, which can be very interesting and very exciting. So here is my presentation. Thank you.
Okay. Thanks very much, Shi. Right, I've got a question for you, mate, which I'll ask. Then I'll come to Stana, then to Bauman, and then to Donya. If folks, you can be as ready as you want to be. Shi, two questions. Actually, I think I'm allowed to now. And one's possibly a little bit unfair, but you've demonstrated some pretty good correlation between the additively manufactured steel and normal steel. Have you checked the ductility? Ductility is quite an important thing of any steel connection. We're normally looking for 15 to 18% between yield and when things break. What sort of figure are you getting from this?
The ductility of this steel is not the focus, but we did pay a little attention to the ductility.
Yeah.
It's not as ductile as mild steel, normal mild steel, but it's, well, let's say fairly ductile.
Yeah. Okay. And second question, as you may not be able to answer this, it's an unfair question really, but would you anticipate now, I mean, the other criterion we would normally design steelwork for is a fatigue, a sort of fluctuating loads, and you might anticipate that perhaps additive material might behave slightly different in those circumstances. You won't have an answer, but we may have a feel for where that could go in the future.
Yeah, it's actually quite an interesting story. One of my colleagues is currently investigating the fatigue phenomenon. But to be honest, this is not part of my research, so I don't know the real answer to that question.
No, okay, but that's fine. I accept that. Okay, right, Stana.
Okay, hello. And my question is related to your future FE modeling. So you mentioned that you are going to follow this up with some FE models of the setup which you investigated. Can you tell us how you plan to do that modeling? I mean, is it going to be some kind of commercial software, and what the main kind of inputs you will have to take care of?
So I'm actually doing some sort of simulation now, and I'm using Abacus to do the simulation. And I didn't follow what kind of inputs you mentioned. What does that mean?
Okay, so I guess the main challenges which you expect in the modeling, what would they be?
So I would simulate the test setup exactly as the one I showed. One plate connected to two high-strength steel plates with one high-strength steel bolt. Perhaps using symmetrical can simulate just quarter of it, but basically this setup.
Okay. And the material properties are all under control, right?
Material property, I'm going to use this one material property, and I'm planning to include the fracture simulation since we can find many fracture as a test outcome.
Okay, so ultimately, what do you hope to achieve then? Like, which kind of recommendations do you think you will be able to build from this research?
So, as I mentioned that before, WEM can be a very suitable method for connection design. And to do so, we need to have some fundamental knowledge about how this WEM connections behave. This lab shear can provide some basic information about this shear out failure, net section failure, bearing failure, and to provide suitable design equations for the future application.
Okay, thank you very much.
Thanks.
Yeah, sure.
Bauman, very quick one.
Yes, very quick one. You mentioned in the future you're looking at optimization of these connections. My question is, what actually you're thinking to optimize?
So basically, connection design is a very tricky one because connection can form into different shapes in different situations. This connection I tested is just lob shear connection, very basic one. In the future, we may test some T-stop connection and other kind of connection. And on T-stop connections, it doesn't necessarily to be the whole T-shape. It can be optimized into to keep just essential parts and remove the other parts that doesn't really do much things.